One thing that we use the impulse-momentum relationship for is to solve problems like the one I have here. Sometimes we're asked to find the average force on an object during a collision. Either it bounces off of a wall or somebody kicks it or two objects collide. And there's a force that each object experiences during that collision. So here's an example. We have a before the collision drawing up here, where we can see that we have an object, a 2 kilogram puck. This is sort of like a top view on, say, like a pool table or something. And it's traveling at 3 meters per second. And then it's going to hit a 4 kilogram object that's initially at rest. And it's a glancing collision, kind of like billiard balls might do. So it then comes in and then it glancing collision, and it leaves at 25 degrees and 1.99 meters per second, and then it causes the 4 kilogram ball to deflect as shown as well. And our problem is to find the average force on the 2 kilogram puck during this glancing collision given the time of contact of the balls during the collision. So let's see how this will play out. So if we look at our impulse momentum relationship, we know that the average force experienced times time is going to be equal to the change in momentum of that object. So again, this is on a single object. So the average force experienced, in this case, on the 2 kilogram object means that we want to know the change in momentum of the 2 kilogram object only. So we are only isolating just the 2 kilogram object and looking at the change momentum of it. Now these are vectors. So what we need to do is go ahead and divide these into our x and y components. So what we're going to have then is we will have our force average will equal the force in the x direction and the force in the y direction. So we're going to find a f sub x and an f sub y, those combine to make our net force, just like any other vector. So the average force in the x direction times time would equal the change in momentum of the 2 kilogram puck, then in this case, as a function of time. So we would have here then, not as a function of time, of the 2 kilogram puck, then in the x direction, right? So just the change momentum just in the x direction. So that's going to be equal to p final x minus p initial x. And again, that's of the 2 kilogram puck. So we'll do the same thing for y. F average y delta t would be then the change in momentum in the y direction. Again, of just that single object. Even if they stuck together, it would still just be that single object. So one thing that we can do then is write kind of this key result, that the force average in x will equal, and if I look at this expression for the momentum, this is the change in momentum of a single object. So I can pull the mass out. So this would be my mass times my v final x minus v initial x, because I'm looking at just the x component of the force. So this is my change momentum, and then divided by the time. And I'm going to box that. So that's going to be a key result in terms of making this application where I use the mass of the object that I want to find the force on. So if I want the force on the 2 kilogram object, then I use the mass of the 2 kilogram object and then the change in velocity of the 2 kilogram object all over the change in time. And then I'm going to write it again for the y direction would be the mass times v final y minus v initial y all over the time. And that then gives me my total force average, which would be the f sub x comma f sub y, and I would just report it in component form. So let's do it for this problem and see how that works out. So the mass in question for the x direction, for both of them would be 2 kilograms. And then for the x direction, v final x, so the x component of the final velocity. So if I scroll back up here and I look at the x component of the final velocity, well, that's going to be, for the 2 kilogram puck, the x component of the final velocity. I know the velocity is 1.99 meters per second, and I know the angle. So the x1 would be 1.99 times the cosine of 25. And the initial, it was just headed entirely in the x direction. And that was just the 3 meters per second. So if I go back to where I was down here, then I can say that v final x would be my 1.99 times the cosine of 25 degrees, and then minus v initial x, which was just equal to 3 meters per second, because it was headed horizontally to begin with. Then I'm going to divide that by my time, which in this case I want to change because I'd like to end up with newtons. So I'm going to change my milliseconds to seconds. And if I do this, and I had already done it previously, I will end up with a negative value, and I'll discuss that in a second. It's going to be on the order of 79.8 newtons. So that's going to be my x component of the force that was experienced by the 2 kilogram puck during this collision. And it's negative because it's pointing in the negative x direction, meaning that it's got slowed down a little bit in the x direction, which makes sense because it hit this other object that then started moving in x. So it lost some of its x momentum. It has a negative force in that direction. And then in the y direction, we imagine that it might actually gain some because it had no y momentum to begin with, and then it got some. So it got a little bit of a force, a positive force in the positive y direction. As for the y direction, let's just plug those numbers in. We have the F average y. Again, we use the mass of the 2 kilogram. V final y, it would be 1.99 sine 25 now. And these are both positive because I'm headed in the first quadrant. And then minus V initial y. The initial y, it's headed horizontally, the initial y is 0. It didn't have any initial velocity in the y direction. All over the time. And then that's going to give me my y value, which is 56.1 newtons. So my final answer then is that the force on the 2 kilogram during the collision would be negative 79.8 I hat plus 56.1 j hat newtons. And I can box that, and that's my result. All right, so again, key idea being that you break the impulse momentum relationship into components. You focus on a single object, and then you write it out and find the 2 components of the force that the object experienced during the collision. Let me know if you have any questions.